So in this class we will be doing n-grams language modeling. So n-gram are actually probabilistic language models and are very strong, were very strong language models around 10 years back, and currently we have much stronger language models that are neural network based language models such as word2vec, fast text, but these are the basic probabilistic language models that were into existence around 20 years from 1990 onwards till 2010. They were quite extensively used, and in most of the applications of NLP they were employed. And but due to advancements in neural networks in past 10 years, the language models based on neural networks are now quite into existence, and they are into the applications. But the base of those neural network based models is also these kind of probabilistic language models. So we will see what are the n-gram language models, and let's see initially, like, why do we require these kind of language models. So the language models are actually used to assign a probability to a given sentence or sequence of words, right? So we need to represent a sentence or some language with the help of numbers in order to use it in machine learning, right? So we need to express the language or the sentences in the form of numbers so that we are able to use it, or we are able to give it as an input to the machine learning algorithm, right? So what are the different kinds of applications in which we could use them? So we can use them in machine translation. Suppose a word is translated into, a sentence is translated into these two, high winds tonight and large winds tonight. So you see this is very little difference here, right? So whichever will have the higher probability will be the correct one, right? So how we are getting this probability we will see later. Similarly, in case of spelling correction, right, we can have this. So this we see here, this is a mistake here, so the probability of this mistaken word will be less than the probability of actual word. And in speech recognition also, I saw a wine, eyes of an an. So when converted into the sentences, the speech may be converted into these both, right? So higher probability must be taken again, and in lots of applications, in particularly all the applications of NLP, we use the language models, and somewhere or there we employ the n-grams currently also, right? So one question you might have in your mind, that in the previous classes we did the maximum matching algorithm, and we did the edit distance algorithm. So we could do all these things with the help of edit distance algorithm. So edit distance algorithm is a distance based algorithm. We discussed there also that we could find out the distance between the original one. So if this is the source sentence, I will find the distance between this one and distance between this one. Similarly, I'll find the distance between this one and distance between this one, and whichever is closer to the source one, that must be the correct one, right? So source, or this may be a true one. So we could do that way also, but those are more older algorithms, and that are distance based algorithms. So distance based algorithms or positional algorithms are not that much efficient when we compare them with the probabilistic algorithms, right? So the probabilistic algorithms are more, you know, uh, more powerful, more efficient than some simple distance-based or positional algorithms. The distance-based algorithm are those algorithms that work just simply counting the distance between some points or some data points or some vector or something like that. So probabilistic algorithms actually calculate the probabilities, right? And these are most often seen that these are much more efficient than distance based, right? So the probabilistic language models actually compute the probability of a given sequence or a sentence or a sequence of words. So we say that the probability of a given sentence is equal to the probability of all the given words present in it, right? If a sentence is having, suppose, n words, so w1 w2 dot 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 wn, so the probability of whole sentence will be the probability or the joint probability p of all of these separated by comma, right? So we extract each word as an individual random variable. This is an individual random component, right? Random variable, and then we can calculate the probability of all these. So this is actually the probability, or called as joint probability, of n variables. We are having n variables, and this is the joint probability. This is joint probability. So you must have studied the probability like p of a. So this is probability of a. This is p of b is the probability of event b or variable b, and p of a comma b is the joint probability. Like these a and b have to occur together, right? So in this case also, in language case or sentences, so these all words are occurring together in a particular sentence, right? If I take the sentence, suppose probabilistic language modeling, I take this example. So these three sentences, probabilistic language modeling, are these three words are occurring together, right? So for this we can write p of w1 is equal to probabilistic w2 is equal to language, w3 is equal to modeling, and then we can calculate the joint probability of these three collectively, right? These three all are occurring together, so we calculate the joint probability. This is one way. So another way could be of finding the conditional probability, the probability of particularly an upcoming word, right? So upcoming word means that we are having in this particular example, we are having 5 words in this form: w1, w2, w3, w4, w5. We are having 5 words, and this is the upcoming word. So we initially we are having 4 words, and we just to try to find out which is the 5th word, which we try to find out this one, or we don't know, we are trying to somehow trying to get which word this w5 could be, right? So in those cases we employ another kind of modeling, that is conditional probability based modeling, in which we calculate the probability of an upcoming word given the previous words, right? So this is actually the p of w5, probability of w5, given that w1, w2, w3, w4 are occurring, right? So right, so we can have this p of w or p of w n given w1 to n up to n minus 1 can be called as language model, right? Some people initially represented the grammar with the help of probabilities, and you can call it as a grammar, but language model is a more kind of common term, more standard term for these probabilities, right? So how to compute the probability? Suppose we have this sentence, its water is so transparent that. Okay, so we have this sentence as is equal to, or let's call it W is equal to, its water is so transparent that. So we are making an assumption that we know the probability of these individual words. We know the probability of its, we know the probability of water, we know the probability of is, and so on. So we will see later how we calculate these probability of individual words. So when we have to calculate the probability or joint probability of a given sentence, right? So the intuition says that we can apply directly the chain rule. So what is the chain rule? So the chain rule is a general rule of probability in which if we are having n variables, right, so we can calculate the joint probability by decomposing it into smaller probabilities, right? This is the probability of n variables, and we decompose to probability of n minus 1 variables. So this is a probability that is involving n variables, and we decompose it to n minus 1 variables, right? So in this way we can reduce it. So p of x1, x2, x3, x4 dot 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 xn can be written as p of the first variable, okay, multiplied by p of second variable given the first one, okay, then the third variable given the first two, right, in this way, and then and so on. So the next term here that we could write would be p of x4 given x1 comma x2 comma x3, right, multiplied by p of x5 given that x1, x2, x3, x4. Okay. So in this way we can calculate the probabilities, right? This is the chain rule, general rule, that is applicable to any kind of problem, and that is general probability rule. We are not applying any assumption here, we are not applying anything. If we have to calculate the probability of n variables in joint probability, then we can apply this rule. And this is an example with 4 variables, p of a dot p of b given a dot p of c given ab dot p of d given abc. So we can do it in another way also. We can write this one as in another way, that is p of the first variable given the rest of the variables b, c, d. This is, I am telling you, another method to write, because this is not the only one decomposition, or this is not the only one decomposition. This decomposition can be done in many ways. I take the p of x2 here in place of x1, then I can start the decomposition also, right? So there can be lot number of decompositions for a given sequence of variables. So p of a given b, c, d, then we take these leftover variables here, right, and then we apply a shorter conditional probability, that is we take b given c comma d, right? So we apply only b, c, d in this term. Similarly we apply c, d in the next one. So p of c given d dot p of d, right? So now you see that this one is different one, this one is different one, and if I want to write the same expression or same decomposition with the help of this kind of methodology, so I would write p of d. I will choose one variable, I choose d from here, p of d, and given the rest of the variables, right? So I choose any one variable and condition it on rest of the variables, p of d given a, b, c, right? Then again from these 3 I choose one, I choose c, right, and condition it on BC. Then I choose here B, condition it on C, then I choose here, I am left over with, sorry, this is not B, this is B given A, this is C of C given B comma A, right, and this is B given A, and this is P of A. Now you see the order here is different. P of A is also present here also, P of A is present here also, B given A is present here also. So order is different. So there are two ways in which you can remember how to apply the chain rule, right? One is this one and another is this one, right? So both will lead to the same decomposition, and depending upon the choice of variables we can obtain different decomposition expressions, right? So for this one we can have P of x2 dot P of x1 given x2, right, dot P of x3 given x1 x2, right? So you see here this part has changed. In this way we can again we can change it little bit. I say P of, I initially choose x2, then I put x1 given this term, right? So I may choose here some x3 also. In place of x1 I may choose another one, x3 given x2, right? Then I may choose suppose x5 given x2 x3, right? So again by the choice of variables, and at the last I will be left with xn given all, x1 dot 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 xn. So it is again the choice of variables that may lead to different decomposed expressions. Right, so for this we can write the, again apply the chain rule here. So P of its dot P of its given water, sorry, P of water given its, water given its, then I again choose the new one, P of is given its comma water, then again I choose a new one, P of so given its water is, and so on in this way, right? So you see here for a given single sentence there are a lot of probabilities involved in the chain rule, and this task may be a very cumbersome task. You know, I may have to find around for these 1 2 3 4 5 6 words, I may be here having 6 terms, right? So and I need to calculate the probabilities of all these 6 terms, and again the problem here is that for the larger one, for this one I have to again decompose it into some smaller, for again, and I have to reach to this single one, or at max at this one. Okay, so this becomes a very cumbersome task. So chain rule is by intuition we can apply, but this is not so practically possible to calculate the probabilities of the sentences. So you see here by applying the chain rule we get this one, right? So we get 5 terms here, and now in order to calculate this one we have to again decompose, and or if we even don't decompose, then calculating this probability value, or for this term which is having large length of sentence will be very low, right? So this sentence, that means its water is so transparent, this whole complete sentence may be only present once in the whole corpus, right? So its frequency of, as we move towards the large size of sentence, the probability of that particular sentence will be very low. Why? The probability is based on the number of counts, and the count of this sentence may be only once or twice. So this term will be of very low probability, and the overall probability will be very low. right? And it may be somewhere near to 0 even, right? So we need to do some kind of assumption, right? So in order to calculate the probability through counting method, we could just calculate the probability of count of wi comma wi minus 1, that is, so this is actually the count of both, right? So we are actually here trying to calculate the probability of any of these kind of terms. So we can write the probability of p of wi minus 1 comma wi divided by wi, p of wi, right? So here, so this, we are just assuming that the sentence is in two parts here, like this, where p of I minus 1, this is I minus 1 and this is I. So probability of this p of I minus 1, sorry, it's not the probability, this is actually the probability. So this is the count, right? Count. So count means how many times the word wi and wi minus 1, or in this, according to this formula, how many times word I minus 1 and I occur together, right? How many times word I minus 1 and I occur together, that is the count of both collectively divided by the count of how many times the word I minus 1 occurs. So this is actually I minus 1, right? So in this way we calculate the probability, okay? And when this becomes too long, so it means that this count will be very low, and this count will also be very low, and the overall probability will be a not very much satisfactory, right? So not too many possible sentences will be there, so the probability will be so why probability will be low? Because we never see enough data for estimating these, so we don't have enough data. So we would like to generalize this formula, we would like to generalize this by calculating the probabilities of small sequences, right? So the Andrew Markov said that we may have some simplifying assumption, and we may assume that the probability of this whole particular term or the sentence, or the probability of the followed by its water is so transparent is somewhat equal to probability of the followed by that. So this is an assumption, right? Or the followed by just a single word, or the followed by just two words. So this can be called as the bigram probability, call it a bigram probability, and we call this one as the trigram probability. Right, so in place of going so long sequence, we just assume that the probability of the is conditioned on just only a single word, or 2, 3 or 4 words, right? Not the complete length of sentence, right? And we can see that this is working very fine, and it's simplifying our job of calculating the probabilities, and it is working quite well. So we just approximate all these the probability of the given sentence as probability of wi. So when we write it like this, probability of W1, W2, W3, suppose you have 4 words, can be written as P of W1, right, multiplied by P of W2 multiplied by P of W3 multiplied by P of W4, right. So this is the joint probability, and we are decomposing it into, when we say by chain rule, right, we will write here as W2, W3, W4, right, and we will write here W3, W4, and we will write W4 here, and we will be left out with so this is the chain rule. But when we apply the Markov assumption, we will say that we are just assuming that this whole term will be replaced by P of W1 given W2. This term will be replaced by P of W2 given W3, and this will be just same because there is only a single word that is present here, 4, and this will be a simple one, that is W4, right. So we see that this part has been done away with, this part has been done away with, and we are left out with the simple probabilities that is involving only 2 variables, that is the bigram probability, right. And we can again have some small sequence if we are doing it with the help of trigram probability, or just having 2 words preceding it. So what does this mean? I will again explain it. So it means that probability of W1 followed by W2, W3, W4. So if there is this little mistake here, I should write it again. What is the mistake? Because this is the sequence of sentences W1, W2, W3, W4. So I should maintain this sequence. So I would write it as W4 is followed by W3, right? So probability of W1 followed by nothing. So just write it the other way around, multiplied by probability of W2 followed by W1, right. So W2 is followed by W1, the probability of W2 given that the W1 has occurred, right, and multiplied by W3 given W1, W2, the probability of W3 given that W1 and W2 have occurred, probability of W4 given W1, W2, W3. So if I am having this, its water is so transparent, so let us take its water is so, right. So P of its water is so is equal to P of its multiplied by P of water followed by its, the probability of water, the probability that water is coming after its, what, right, dot probability of is followed by its water, and then the final term is probability of so followed by its water is, right. So these are 4 terms that we are getting through the chain rule. This is through the chain rule, right. So when we apply this one, this bigram probability, this one bigram probability, we are replacing the whole sequence by a single word, right. So in this case, for bigram probabilities, okay, when we apply this one, P of, so what will be eliminated? This one will be eliminated, and these 2 will be eliminated, right. So here this whole sequence will be replaced by just the last word, the word that is very close to this is the word that is very close to so these two will get eliminated, right? So what will be the left out? P of its, P of water given its, P of is given its, water given its, right. This is not, a little mistake is here again. So water will not be eliminated because it is not close to its. So actually this one will be eliminated because is followed by water. Water is, we see here water is, so here also this will be eliminated, right? So it will be now its dot P of water its dot P of is given water dot P of so given is. So this is its, then water followed by its, then is followed by water, and so followed by is. So these are the bigram probabilities. Similarly, if we go for more high number of sequences, we say that the n-gram size here is equal to actually 2. N-gram is equal to 2 here, right? So we can take n-gram as n is equal to 2, n is equal to 3, n is equal to 4, and so on. We can take the value of n depending upon the requirement. So we can have the value of n somewhere between the actual maximum length and 1, right? So when we take n is equal to 1, it's simply the unigram probability. So probability of this whole sentence will be just probability of all the words. So that is P of W1 multiplied by P of W2, W1 dot P of W2 dot P of W3 dot P of Wn, right? So if this is a sentence, or this is some automatically generated sentence from a unigram corpus, so fifth, and these are the single words, right? So these are unigram model. So we need to calculate the probability of these in case of unigram model, right? So unigram model gives just only the words, right? So these are just single words. In case of bigram model, the probability is Wi given just its previous word, right? So in this case, the probability will be, so the probability will be the collection of two words, right? So here so we can collectively take to these, right? So we can have these two, we can have these two, we can have bigrams like this, right? So probability of new given outside, right? Probability of parking given car, and so on, right? So outside new car parking, lot of the agreement reached. So this is suppose a sentence, and if we have to calculate the bigram probabilities here, or if we have to calculate the probability of this complete sentence, so P of W would be equal to all the combinations up to last P of reached given nothing, right? And the second last would be P of reached, P of mm, agreement given the reached given agreement. P of reached given agreement, right? And the previous to this will be pre of agreement given the. So in this way we can calculate the bigram probabilities, and we can generalize this. We can say that we can have an n-gram language model in which we can extend it to n is equal to 4 and 5 and so on, 6, 7, 8, right? So this kind of language modeling is called as n-gram language modeling, and depending upon the problem that we are solving, we can have the value of n. But we see that this language model has the problem of not able to resolve long distance dependencies. What is long distance dependency? In this sentence we can have an example. The computer which I had just put into the machine room on the 5th floor crashed. So what crashed? Right? The floor did not crash, right? The computer crashed. So this crashed is actually related or dependent on this computer, right? So for long dependencies, this n-gram is not that much efficient, but however we can have for short-term dependencies, this n-gram is quite much efficient and quite powerful, right? So we did this earlier also. We can calculate the probability of a given the word wi, given a word wi, probability of wi given wi minus 1, just its preceding word as the count of wi comma wi minus 1 comma wi given wi minus 1. So the count of both occurring together divided by the count of the preceding word. So these are actually called as maximum likelihood estimates. So maximum likelihood estimate is actually that kind of probability estimate which gives the maximum, which maximizes the probability. So we can have a small examples. If suppose this is a corpus, right? Start I am Sam, and then start of sentence Sam I am, then end of sentence, start of sentence I do not like green eggs and ham, end of sentence. And I have to calculate the bigram probabilities. Bigram probabilities. So what are the different bigram probabilities that will be present that can be calculated with the help of corpus? I will calculate the probability of I am. What is the probability of I am? Probability of I am is actually, bigram probabilities are like this: am given I, right? Similarly, this probability of I given start, probability of this another bigram. So bigram probability is Sam given am, right? So we see that the first one is I given start, then the next one is Sam. So this may not be in any order, right? So these are just the probabilities that can be calculated. So they have calculated in this slide. Some of the bigrams, 6 bigrams, the probability has been calculated. So let's see how can we calculate these probabilities. So the probability of this occurring together, so the count of this start and I occurring together is how much? So in this, for this case, count of start comma I divided by the count of start. So what is the count of start and I? Start and I is, the count is 2, right? We have this one place and another place, the count is 2 here, and the count of start is 3 here, The count is of start is 3 times here, 1 2 3. So this 3 is here, right? So in this way we can calculate all the different probabilities. So Sam, let's take this one. P, do give an I. So the count of I comma do divided by the count of I, right? The count of Wi minus 1 comma Wi. So we can also write the other way. We can also write the count of Wi comma Wi minus 1, or both the ways. Okay, so in the corpus, it is present I do, here it is present, right? So this is only once. The count of I and do is only once here, and the count of I is present 1 2 and 3. So this is 1 divided by 3, right? So that is 0.33. Okay, so this is the way we can calculate the bigram probability. Similarly, we can calculate the trigram probabilities, right? So this is all some things taken from the Berkeley restaurant project sentences. So there is a corpus called as Berkeley restaurant project sentences, okay, in which the words are, can you tell me about anything Cantonese restaurants close by, or tell me about the cheese panisi. And so these are some example sentences taken from that corpus, from Berkeley corpus. So if we see the bigram counts, like from that corpus, we have selected some words. I want to eat Chinese food, lunch spent. I have taken these 1 2 3 4 5 6 7 8 words, okay, and I have created this kind of matrix. This matrix is called as bigram count matrix. So this bigram count matrix actually calculates the bigram counts, right? So these are the bigram counts. These are called as bigram counts. These are bigram counts. These are unigram counts. Unigram counts. So what are bigram counts? The two words occurring together. So this I is occurring together in very small numbers, but I want is that this is having a very very high count in the whole corpus of around this is around 9,222 sentences. The count of I and want occurring together is 827. Similarly, want and to occurring together is 608. To and eat is occurring together is 686, and so on. But we see that lunch and want, this lunch and this want, it does not occur, right? So this matrix is called as bigram count matrix. Similarly, we can draw a bigram probability matrix by just dividing the terms with their respective unigrams. Okay, so if we divide these terms, I want, right, I to, I eat, I Chinese, I spend, right? So which is the preceding word? I is the preceding word, so we divide the first row by the count of I. So when we divide the first row by the count of I, we get these probabilities. Similarly, want I, want to, want eat, want Chinese, So if I divide all these counts by the probability of want, by the count of want, I will get the bigram probabilities. So in this way we divide all these by different. So I am assuming here this as wi minus 1 and this as wi, right? This is wi minus 1. If I do it vice versa, if I assume it this column, this row wise as wi and column wise as wi minus 1, then I can just I have to divide them row wise, right? But I have assumed wi, the preceding word, as row wise and the succeeding word as column wise. So in this way we can calculate the bigram probabilities, and we see there that a lot of zeros are here. When we will draw the matrix of the whole corpus, we will see that this kind of matrix will be a sparse matrix in which there will be lots and lots number of zeros, right? So for a given sentence, I want to eat food, start and end of sentence, start given I want English food, end of sentence is equal to, with the help of bigram probabilities, I will look into the table and write this probability, look into the table, write this probability, and I will write all these probabilities, and I will get this as the total value of the probability. Similarly, I would get these probabilities from that bigram probability matrix. We see that want English is very low probability, want Chinese is somewhat greater than English. Maybe in that corpus some want Chinese word is more common than want English, because this want English, this is the bigram for this one, and for this one the bigram is want Chinese. So when we calculate the probability, we calculate count of want comma English divided by count of want. So the denominator remains the same, but we see that the count of want with Chinese is higher. That's why we are getting a little higher probability for want Chinese, and we see that we are getting this zero probability, maybe the 2 followed by food, right? So food is not coming along with the 2, so that's why we are getting zero probability. Spend want is not, they are not occurring together. And we see want to is a very common term, a grammatical common rule due to that, or to eat is again a grammatical rule. So we are getting very high probabilities for this, right? And with this last one, I given start, so the bigram is start given I. In most of the sentences, whenever we write, we used to write I we start with I, so that's why we are getting a high probability for this one, right? So in this way we can calculate the probabilities, we can analyze all these probabilities, and we can study about the corpus, and we can apply these probabilities into some application we will see later. So the practical issues are there that we don't go for the actual probability values, instead we take the log of these probabilities, because a small number of when we use these probabilities, we may be dividing these probabilities, we may be multiplying these probabilities. So multiplying these very very small numbers together will be again a very much smaller than these two, right? So that's not practically, again, and we divide a small number by another small number, right? So there are some practical issues we have to avoid underflow also, dividing by a very 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 small number. And then for fast multiplication, we just employ the log, so that we don't have to actually multiply. Instead of multiplying, we can just add the log probabilities, right? So P of W1 comma W2 dot 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 W4 or W3 W4 right? So it can be written as some probability, right? We have W1 given W2 and so on. So these probabilities, so instead of these taking these as products, we take them as log probabilities, log of this whole probability. Log probability of W is actually the log of this P1 log plus log P2 plus log P3, that is log whole of P1 dot P2 dot P3 dot P4. So that is log P1 dot P2 dot P3 dot P4. So what we are calling it as P1, P2, P3, P4. So practically we when we have large size corpus, we don't actually do the raw probabilities or actual probabilities. We take the log of these probabilities so that the computation time is saved and we can do much faster processing, right? So that's all for today.